Okay, thank you. Thank you, Richard, and thank you to the organizers for having me here today. On the left side of this slide is pretty much all the research that I had coming into this project when Richard first approached me. Richard approached me in about 2010, and the question on Richard's mind was, are there any aqueous cleaning conditions that we can use that can mitigate the extraction of surfactants and other materials from acrylic paintings? That's what he was sort of thinking about. And so we decided to investigate aqueous cleaning conditions. We looked at pH, conductivity, ionic strength of these solutions to see if we could minimize, not eliminate, the extraction of these surfactants. And then later, we decided to look at environmental conditions, temperature, relative humidity, to see how surfactant moved in these acrylic paint films. We know it exists as a burden in the bulk of the paint films. It exists as a burden at the surface of these paint films that could contribute to soiling mechanisms. But we really wanted to sort of study this analytically, and that's what I sort of do. So those first two papers there on the right-hand side explore those two concepts. The third paper is actually the result of those first two papers. We could understand something about these aqueous cleaning conditions. We could understand something about the movement of that surfactant. And so we could build a particle emulsion cleaning system that could address these particularly peculiar concerns with acrylic cleanings. The talk I'm going to tell you today is sort of a story of two different paint systems. One is an acrylic emulsion paint system. We use Golden Artist Colors acrylics, and the other is a water-soluble oil paint system, and we used Winsor & Newton Artisan Colors. So two different media, but they're commonly linked because they both contain surfactants that are going to factor into things like soiling mechanisms, how we build these particle gel cleaners, understanding what the organic phase, the silicon phase of these emulsions is going to have to be tailored to be, understanding what the aqueous conditions we're going to use to bring to the surface of these paint films to remove soils. And lastly, we'll look at some model paint systems. We'll look at the effects of cleaning and building these particle emulsion systems on how well they performed, what residues do they leave, and possibly some recommendations for the conservator, considering the nature of the soils, considering the nature of the surfactant on these paint films. It really is a story about soils and soaps in two different paint media. So in considering the two different paint media, we know that emulsion polymerization paints, these acrylic polymers, coalesce. So the mechanism of film formation is coalescence. Particles of acrylic emulsion are suspended in an emulsion by surfactant. The particles grow closer together. They begin to form a film. And then at some point, the surfactant is really no longer needed. The surfactant is left in the bulk of the paint film. It can move to the surface of the paint film, but it becomes part of that artwork. It becomes part of that piece, even though it serves no function after it's coalesced. They're extremely water sensitive, and so we have to take that into consideration. The water-soluble oils, the Winsor & Newton Artist Colors, these can either be hydrophilic modified oils to make them water-soluble, or we can use surfactants in that oil paint in order to make them water clean up with water thinned. There are also water mixable thinners, which are special thinners used for these artisan colors. They contain surfactants of their own. So both of these paint systems are going to be laden with surfactants. In the oils, they polymerize as traditional oils would. Okay? We're going to polymerize across double bonds. We're going to form this extended network of an oil. Okay, but in both these paint systems, surfactant is going to be left behind. What is the nature of that surfactant? So I use mass spectrometry to answer these type of questions, and I use surface mass spectrometry in particular. So I can look at surfactants in the surface, or if we extract them in cleaning solutions. And what we find in these Golden Artist Colors, and people have known this, Bronwyn and Ormsby has reported extensively on this, is that they contain these alkyl phenyl ethoxylates. Okay, so that aromatic structure that's incorporated into that surfactant, the alkyl phenyl portion, that becomes extremely important, we found, in the soiling mechanism. In the Winsor & Newton Artisan Colors, we find a different surfactant. We find these alkyl ethoxylates, these lauryl ethoxylates. So there's no phenyl incorporation there. Okay, 2 non-ionic surfactants, we should have similar cleaning mechanisms, similar soiling mechanisms. But it doesn't appear that way when we conduct further studies. How do we soil these paint films? Well, Richard and I developed this sort of nuclear soiling mechanism where we use fingerprinting powder. This is just lycopodium spores. These are carbon-based fingerprint powders, but they're kind of unique. They're tagged with a fluorescent agent, so we can visually monitor their movement by this fluorescent tag. And that comes in handy for when we want to look at how surfactant moves between the bulk of the paint film and the surface of the paint film. We analyzed 7 acrylic colors and 6 water-soluble oil colors. Those are sort of reported in the communication that we published for this conference. I had a video, but it didn't work, so this is the result. What's really interesting about using surface mass spectrometry in paper number 2 we published on the environmental studies is that we can monitor that surfactant, how it moves with temperature and relative humidity. And what we find is that as we increase temperature, the surfactant actually moves into the paint film. We can measure its disappearance from the surface. As we cool these paint films, the surfactant comes back out and comes to the surface. Unfortunately, it occurs sort of maximally around room temperature, so that these environmental conditions that museums and paintings are sort of displayed, stored, held at, any cycling about that point is going to drive surfactant to the surface and back into the paint film repeatedly over the course of years. This is just over the course of a day. We've fingerprinted powdered the surface of this paint film, and then we can monitor it. And as you see, the luminescence, possibly, yeah, you can see. The one on the left is brightly colored. So as we increase the temperature, the luminescence on the surface of that paint film decreases, which means the surfactant we know is going into the paint film, but it also means that the soils are moving with that surfactant into the paint film. And this was sort of an aha moment for Richard and I, because we had long known the movement of surfactant, but we really wanted to associate how surfactant moves with soils. Is it really that soiling mechanisms in these paint bodies? Could it be triboelectric? Could it be that they're inherently soft? But this was sort of one of those moments where we saw it move and we saw the soil move. And what's peculiar about this is we can bring it back out. As we decrease the temperature, we can bring those soils back out to the surface. But you'll notice, just over the course of a day here cycling, we can't bring them fully out. So the luminosity at the start of the day versus the luminosity at the end of the day is much less, which means we've inherently moved soils irreversibly beneath that paint film. And that was some evidence that this could be the soiling mechanism in driving these soils into these paint films. The other peculiar thing that sort of appeared is that we cycled films through temperature and relative humidity. And what we noticed in the golden artist colors is the appearance of these glossy spots. Now, these would start out as very small dots that would agglomerate into tiny spots that would agglomerate into larger areas of the acrylic paint film. They're glossy. We see specular reflection at the surface. What's happening here is that soils are being driven deeper and deeper into that paint film, and the surface of that paint film is becoming deplete of that soil. In the matte areas, the darker areas in this photograph, soils exist at the surface. We can see that there's specular reflection, or diffuse reflection sort of occurring here with the soils that remain at the surface. Those are going to be easier to clear. We knew that. We didn't notice this, cycling temperature and relative humidity, with the Winsor and Newton artisan colors. We didn't see these spots appear. The reason that we came up with for why these spots appear is because of associated soils. We know that cycling temperature and relative humidity is going to bring surfactant into the paint film, dragging with it particles that are associated at the surface. Beneath the surface, then, a huge reservoir of surfactant exists. And we can have these associated soils on the left here that are bridged by, actually, these alkyl phenyl ethoxylates. And the phenyl group here is important for that bridging. In nanoparticle formation, this has been reported, that these Triton series of surfactants can actually associate strongly soils. We can see this in a laboratory scale by just simply dropping some Triton surfactant into a dispersed soil and watch it agglomerate. So we know we're going to have to overcome these associations that are deeper beneath the surface of the painting. At the surface of the painting, we probably have a situation similar to on the right, where carbon particles are unassociated. Surfactant then is keeping these apart. When we look at ATR, FTIR of these spots versus the matte films, we can sort of validate what we see. We see that on the surface there is surfactant in these unassociated soils. Beneath the surface, at the glossy spots, we see associated soils and the disappearance of surfactant. So we're gaining some analytical evidence for what might be a soiling mechanism and how associated soils are going to be quite difficult to remove in these paint films. So like Richard said when he started out, we went down a river and we had to turn back from this river. We sort of went down this path with these particle cleaning emulsions, and we realized that they're not strong enough. We built them around things that we know, these D5 cyclomethicones, the KSG particle emulsifier. We started out with many different particle emulsifiers. The right aqueous cleaning conditions to minimize swelling, minimize extractives in these paint films. But you can see we can clean those unassociated soils at the surface, but deeper, we can't remove those associated soils. We have to devise a cleaning system that takes that association into account. And so that became quite a thing to do. So it's nice following Chris, I'll say that, because he did a great job of explaining these Shinetsu KSG materials. We work with this cosmetic company, Shinetsu. There's a wide variety of particle emulsifiers that they produce. We evaluated many. One of the ones we particularly like is this KSG 350Z. There are many others that are suitable for different types of cleaning systems that you can build as conservators. But the nice thing about them is that if you look at that phase diagram on the right-hand side, there's a huge working area where you can work water in oil emulsions at very high aqueous percentages, up to 95% water. You can make very thick, creamy emulsions. You can also work at low aqueous percentages, down to about 40-30% aqueous. So you can either work high water or low water, depending upon the water sensitivity of your surface. And you need very little KSG 350Z, on the order of 5 to 10% max. Here's some of the other particle emulsifiers we've looked at. The KSG 210 is pretty versatile as well. The KSG 45Z we've had a lot of success with, as well as Velvasil. So it's really understanding the association of these soils and what you're going to have to build into a cleaning system that might guide you in picking a particle emulsifier. But there's many out there from a company like Shinetsu. When you look at these microscopically, they're quite interesting. They're surfactant free. We already know that there's a huge burden of surfactant, both in the Winsor and Newton artisan color, the water-soluble oils, as well as the golden acrylics. We don't want to bring any more surfactant to the surface of these paint films and create any undue soiling or synergistic effects between surfactants. So in the lower left-hand corner, you can actually, you can see the division there. Those particles surround an aqueous core. So they wet 90 degrees into the aqueous phase and 90 degrees into the silicone solvent and hold water trapped and hold it back from a surface. We're going to have to make that water work to get at the surface to clean these paint films. One note on mixing. If you mix them by hand, shaking, sort of as Chris does, you're going to wind up with a situation that you can see on the left. You're going to wind up with an emulsion. It's going to look nice and creamy, but your particles are going to surround much larger aqueous phases. What Richard and I tend to do is use mechanical mixing, paint shakers, more sort of energy going into the mixing process to disperse that aqueous phase through a larger percentage of that silicone solvent. Chris's idea is actually pretty good, using that syringe. It's something I didn't quite think of, but to aspirate it and do something like that, we need to find a way to bring that into finer and finer droplets so that we can increase the coverage on the surface of these paintings. So, we know that we're going to use particle emulsifiers. Now we have to consider what sort of silicon phase or organic phase we're going to build these emulsions around. D4 and D5, historically, that's what we want to sort of start with. We saw it wasn't strong enough to remove that associated particles from beneath the surface of the painting. They work fine on the unassociated particles on the surface of the painting, but once something moves beneath that paint layer, we need to use something stronger to overcome that association of the phenol, the aromatic association. And so something like toluene worked pretty well, about 25% toluene. Unfortunately, it softens paint films, so there's not much working time on the surface and it's not going to be a viable solution. So we needed an organic solvent that comprised about 25% of aromaticity. So Richard and I left the day, ate dinner, both got on the computer, started searching that night, and about midnight we came to the same conclusion. We sort of were talking about this at midnight, I can remember it well, that we found this phenyl trimethicone. Richard found it from a cosmetic company, I of course found it from a chemical company, but we were talking about the same material. So either we were both going to be very right or both going to be very wrong. We ordered some, it came in, and we tested it in the lab, and sure enough, it did work. It can overcome that interparticle association, and we can clear those heavily associated soils from the paint film. As Chris said, and as was done on the San Sulpice murals, we rinse with a hexamethyl disiloxane solvent, a D2 solvent, to remove any silicon particles, silicon organic phases, and the aqueous phase. So this is a highly volatile solvent. It's going to dry very quickly. One of the things that is a disadvantage of using the phenyl trimethicone is that is used in the cosmetic industry for hair sheen products. So your glossy, shiny hair is all due to phenyl trimethicone. We don't want to leave something like that on the surface of a painting. It's going to leave a gloss, it's going to leave a sheen that's not going to evaporate. So we need to make sure to clear those using D2. When we build the aqueous phase of these particle emulsions, we have to take into consideration, again, the nature of the paint body. In acrylic paints, we want to work above the isotonic point. We want to work in these hypertonic solutions. So we're not swelling the paint film. We're not bringing water into the paint film because of all the salts in acrylic paints. In the Winsor & Newton Artisan colors, there really aren't going to be a lot of salts left in that paint film. So we don't have to worry about conductivity as much in building the aqueous phase. In golden artist colors, in the acrylics, we know that the existence of polyacidic acids is going to swell the paint film, so we don't want to work at too high of a pH and swell that paint film, make it more receptive to water. And so we have to limit our pH, namely by the pKa of that. In the Winsor & Newton Artisan colors, our pH is primarily limited by the saponification of the triglycerides, so typical oil paint film chemistry. And so there's a workable pH range sort of in both these systems. So now we know something about the particle emulsifier. We know something about the silicon solvent we're going to use. We know something about the pH of the aqueous solution we're going to deliver to the surface of these films. And so when we actually do that, it's kind of gratifying to know that what we think is happening at some molecular level actually happens at the visual level. What we see is that in these two paints considered here, the rest are considered in the publication, that generally in the golden artisan colors, the golden artist colors, because of the presence of that alkyl phenyl ethoxylate, D5 cleaning systems are not going to restore the luminosity, are not going to restore the color. We have to work harder. We have to use that phenyl trimethicone-based solvent system in order to break up those associations. But if we do, we can restore the original color to those paint films. In the artisan colors, because of the presence of an alkyl phenyl ethoxylate that doesn't associate soils, we're not as restricted. We can work in dimethicone solvents. We can work with other emulsifiers. You can use KSG 210. You can use probably Velvasil to build a cleaning system for these type of colors. They're not as restricted because of the presence of alkyl ethoxylates rather than alkyl phenyl ethoxylates. Both work equally as well, but if you don't have to worry about gloss, let's work with the cyclomethicones. When we look at residues by FTIR, we don't find residual silicon peaks before and after cleaning, so that gives us some credibility that we're removing silicone solvents from the surface of these paint films, removing particles, and the UV test as well could lend some further evidence. Because I'm a mass spectrometrist, I do mass spectrometry on the surface of these paint films, and so what we're going to see is that we do get the original gloss back that we started with after soiling, because surfactant does reaccumulate in these paint films. With just a few temperature or relative humidity cyclings, we can get that paint film to appear as it was before soiling. There isn't the presence of these siloxane solvents, so we can sort of monitor that as well, much more sensitively by mass spectrometry. And so what Richard and I would probably propose is that there's two types of soiling mechanisms that are going on in these two different paint bodies. Both contain surfactants. However, in one paint body, we're going to have the associated soils, such as the acrylics with the alkyl phenyl ethoxylates. And we're going to have to work a little bit harder at the surface of these paintings to get those cleaned. We're going to have to devise cleaning systems that include some degree of aromaticity. In the Winsor & Newton Artisan Colors, we're probably working with more dissociated soils because of the lack of that aromatic substituent, where they can be removed primarily from the surface and working with less invasive cleaning systems. In both cases, we're going to do, like everyone has done since we started this workshop, we're going to wet that surface with a cyclomethicone, a D4 or D5. We're going to make that cleaning system work hard to get at the surface, hold it back, build in some working time on these surfaces. We're going to build the cleaning system appropriate to the soiling mechanism and the surfactant. And then when we clear, we're going to rinse with D2. And then potentially in a few temperature or relative humidity cycles, we can get that gloss back and recover that. So Richard and I would like to thank the following people in my lab and at Winterthur, as well as the chemical companies that were kind enough to work with us in making this research possible, as well as the NSF for funding our research. Thank you.